Hi everyone, welcome back to our channel. I hope you and your family members are doing good because that is the most important thing, and for rest we are here to talk. So we were following our pattern wise DSA sheet. In this we were doing 3 topics and we will follow the pattern BFS and we'll solve another question. Let's solve top view of a binary tree in this video. So let's read the problem statement. It says we will be given the root of the binary tree and our task is to return its top view. Now let's see what's top view. Top view of a binary tree is the set of nodes visible when the tree is viewed from the top side. Okay, so for this tree, if you see, first 2 will be visible, like from left to right we have to see. 2 will be visible, then 1 and then right, which is 3, correct? So 2, 1, 3 will be the output. Now in example number 2, first 40, then 20, then 10, then 30, then 100. Why? 60 and 90 will not be visible because they will be hidden below 10. Okay. Now let's see the constraint. It says minimum number of nodes will be 1. Okay. And maximum number of nodes will be 10 power 5. So if you are looking for any type of code which will take n square time complexity, then 10 power 5 multiplied by 10 power 5 becomes 10 power 10. And you know, because you have watched our video on time and space complexity, if not I'll attach the link somewhere here, key beyond 10 power 8 it's not safe, and for sure at 10 power 9 and 10 so it will give TLE because 10 power 8 operations are allowed. Okay. So we have to optimize and we have to look for something linear, like a linear time complexity code. Okay. So let's assume this tree. We have to print the top view of the tree. So 4 will be visible, correct? Then 2 will be visible, then 1 will be visible, then 3 and then 8 and then 9. 5 will be hidden, 6 and 7 will not be there, okay, will not be visible. So what logic we should apply such that these elements are visible? So as of now in tree data structure, we have learned 2 types of traversal, correct? DFS and breadth first search. Okay. So if depth first search, if we'll go this way, this way, this way, okay, then how we can assure ki we need not to take this 5, we need not to take 6 or 7. Similarly, if we are going through BFS traversal, still we are not sure. Okay, if you are thinking ki let's print the corner elements because that will be the view, okay, as of now though it is correct, but if you will print the corner elements, 5 will also get included, but as you can see from the top view it's not visible. So for sure when it is about vertical level, okay, vertical view, we cannot go for, or we cannot think our idea as per the level order traversal. Okay, so how we can think? Let's see. So if you remember in our level order traversal using depth first search approach, what we did ki how we'll remember ki 2 and 3 belongs to same family. So we had given one variable that is level. Remember ki from node whenever we were traversing towards their left and right child, we were giving the parents level and +1 to their children's. Okay. When we have to think about level, we did that. So similarly, don't you think here also we have to think, but instead of horizontal level, we have to think about vertical levels. Can I say that? Means if let's say we give vertex 0 to it. So if it is at 0 level, towards its left side, can I say it will be -1, negative, and towards its right side it will be +1. Think about the x-axis. Now if it is 0, then towards its left -1, towards its right +1. With that analogy we are doing. Okay. So if we are calling the left and right children's, what will give? Parents node -1 for left and parents vertex +1 for right child. Okay. So its vertex will be -1 and its vertex will be +1. Similarly, from 2's perspective, this is a left child, so -1 which is -2. Okay, now this will be -1 +1 which will be 0 for it. Okay. Now similarly for 3, parents node is +1 and -1 will become 0. Similarly this will be 2. Similarly for 4, 5th will be -2 +1 which is -1, correct. Now this will be 3. Okay. Okay. So if we will traverse like this, ki for -2 vertex, how many nodes we have? Think again. For -2 we have 4. Now for -1 we have 2 and then 5. Now for 0 we have 1, 6 and 7, correct? Now for 1 we have 3, yes, that's it. Yeah. Now for 2 we have 8, and now for 3 we have 9. Now think again, what was the expected output? Output was 4, 2, 1, 3, 8, 9. Can I say that? All what like top view nodes, these are the nodes, correct? So if you see here, what are these? These are nothing but 2, 4, 2, 1, 3, 8 and 9. So if we can do the traversal, and for every node, if we have the vertical indexes, and if we somehow able to save in our map, or you can say array, okay, and from every vertex we will just take the first elements. We'll just take the first elements, and then that will be our answer. I just proved you how it worked. Okay, first initially we started from 0 vertex as a node. Left we have given -1, and right we have given +1. Okay, and as per these vertex we'll fill the elements, nodes, and we'll traverse, and we'll just pick the top ones, and these are our answers. Okay, now the concern is ki how can we do it, via DFS or BFS? It is possible through both the ways. Okay, so let's see via BFS first, and then we'll see via DFS. So what we have learned in breadth first search, key first we'll make a Q data structure, correct, and in Q first we'll insert node. But earlier we just have to worry about node, but now we have to worry about what? Vertex also. So for every node we have to insert 2 elements, first node and then second, can I say vertex? So for that, Q in Java does not support like multiple elements insertion at the same index. So hence we have to make pair. Okay, so we can make pair for it. First node will be entered, and then its vertex. Done. Now what we'll do, ki while our Q is not empty, Q is not empty, what we'll do, one by one we'll pop each elements. When we'll pop this, we'll see ki what is the vertex for it. So initially we'll insert what? Node, which is root, and vertex will be 0. Can I say that? So first we'll insert 0 as vertex and root. Now what we'll do, we'll pop, type will be pair, because pair will define, and it will be, let's say, current. Okay, current. And now we'll pop from Q, Q dot poll. That's it. Now what we have to do, we have to insert this node with the help of this vertex. But where will insert? For that we need a map, correct? So we'll initialize a tree map somewhere here, okay, of type integer vertex, and then node value also integer and map, okay, like this. Now as we have popped, so what is our task? See, if you remember, this is the first node, okay. So as of now in the map for vertex 0 we have no element, correct? So this will get inserted. Now similarly, when we will go to insert this, as of now for -1 in the map we have no element, so 2 will get inserted. Now as it is level wise, so we'll go on 3. Again for 3, vertex 1, for 1 we have no element, so it will also get inserted, correct? Now next time for the next level, for 4, which is vertex -2, no element, so 4 will get inserted. But wait, now when we'll pop 6, for 6 vertex is 0, and for 0 1 already has been inserted. So do you really think we need to insert 6 or we need to insert 7? I don't think so, because we are going through level order, and if for any vertex we have already found any node above it, so for sure that will encountered as top view, and 6 and 7 will get hidden, correct? So I simply write ki if our map does not contains key, if our map does not contain that key, what is the key? Which is current dot vertex, or let's say current dot v, which is vertex, okay. Now if it is not present, then for sure we have to insert this node value for that vertex, correct? So what we'll do, ki map dot put for what? Current dot v. What do you want to put? Current dot node dot value, correct? Why? Because current is a pair and it is holding 2 elements, this root and this, correct? So you can say root also or node also, whatever it is. Then current dot root or node, whatever it is. So current dot root, and then its value we have to fetch to store it. and current dot v, directly it is an integer, so that's why current dot v. So what we do in our map for vertex 0, because it was not present, we have inserted node value 1, correct. Now what is the task? Insert its left child and right child, correct. So what we'll do, if current dot node dot left, if it has left child, then in queue we will offer. In queue what we will offer? Again we have to offer by taking a new pair or creating a new pair, correct. So we'll write new pair. Now first node and then its vertex. So node will be current dot node dot left, this will be node, and vertex will be current dot value or v, current dot v vertex minus 1, because we are going towards right side, left side. Now if we want to go towards right side, means current dot node dot right. If this child is present, then again in queue offer what? New pair, and in new pair the first node will go, and what is a node? Current dot node dot right. And what is the first vertex? Current dot v plus 1. Why? Because we are going towards the right side. So what will happen in the queue data structure? In queue, first we had 1 and its vertex 0. Now we popped. Now its children will go, which is 2 vertex minus 1. Similarly 3 vertex 1. So when we will pop 2 vertex minus 1, then this minus 1, which is a vertex, this is not there in the map. So in the map we'll put, by the way, will come outside this, correct, and this line of code is outside the first if case, okay. Now these are on the same levels, okay. So first we checked if minus 1 has not been inserted. Yes, it is not present in the map. So in the map we'll put again, what we'll put for minus 1, what we will put for minus 1, we will put the value which is 2, correct. Now we will insert in the queue their children. So their children will be what? 4 minus 2, what? 4 minus 2 and what? 6, 0, correct. So now we'll pop 3. For 3 again vertex has not been inserted. So for 1 we will insert what? 3, correct. Now next time 4 will pop. For minus 2, 4 will get inserted, okay. Now fourth children will also get inserted, which is 5 but index minus 1. Now when we'll pop 6, vertex is 0, 0 is already present, so we don't want to push. Why? Because 1 is the node which will be visited first or viewed first from the top. 6 will definitely be hidden, okay. So that is why if that key is already present, then don't override that value. So this will be our top view code, okay. So now let's dry run all. So 6 will also get popped, it will not get inserted, correct. Okay, my bad, when we popped 3, so 7, 8 will also get inserted before 5, okay. So let's first pop all this, okay. Now, so after popping of 3, we inserted 4 with minus 2, correct, and 6 with 0. Then like 3 was sitting here, when we popped 3 also, then its children will also get inserted, which will be 7 with 0 and 8 with 2. Okay. Now when we'll pop 4, then only its child, which will be 5 minus 1, will get inserted. Okay. Now what we'll do, we'll pop 6 as shown. 6 vertex is 0, which is already visited, so we'll not save. Now 7 vertex is also 0, will not save. 8 vertex is 2, so 2 has not been inserted, so for 2 we will insert 8. Okay. Now 8 will also pop, and its children 9 will insert with vertex 3. Now when we'll pop 5, minus 1 has already been there, so 5 will not get inserted because 5 will be hidden by 2. Okay. Now when we'll pop 9 with 3, correct, then 3 has not been inserted, so for 3 vertex 9 will get inserted. For 3, 9 will get inserted, correct. Now this is the map we have for every index, the top nodes we have. Now we'll just iterate in this, okay, and at the end we will return this in the array list form. That's it. So what is the time complexity? Every node we have visited for first time, correct, in the BFS approach. Okay. And what is the space complexity? We have inserted every node in this queue. Okay. So if it is a complete binary tree, what will happen? All node will get inserted, and in the worst case, last level of nodes will get inserted in the queue, and last level of nodes will contain n by 2 elements. So hence the space complexity will also be linear O of n. Time will also be linear O of n. So let's write the code for this in the editor. So here is the code what we have. First we'll create the pair, and for every node we will have node and HD. Now inside the top view function we'll create the array list to store the values of top element, and we'll check the base case what if root is null. But as in the question it says the minimum number of nodes will be 1, so in the breadth first search approach we don't need to write this line of code. In DFS it is required. Okay, now we'll create a map and we will make a queue, correct? Inside it we'll offer first root with index 0. Now we'll keep popping elements until it is empty. First we'll pop and check if the map, tree map, does not contains that index, then first value we will insert, and this line of code is to only insert the left and right child. At the end we will just iterate in the map and contain or store all its values, and that we will return. So this is our BFS code in Java. Let's run this and let's submit this code. Okay, so this is your Java code. If you understood, here is your C++ code and here is your Python code for the similar approach. Now we'll discuss the depth first search approach code. In DFS, so it is very easy. Why? Because to store the value also and the horizontal distance, which is vertex, you can say, also we need to create the pair. But in DFS as it is a function, so along with root and along with the level we will send the vertex or HD also. Okay, so we don't need to create an extra pair like what we did in the queue data structure. Okay, so now it is very easy. First we will check what if our root does not exist. If root is null, we will simply return. Why the base case is required in the depth first search? Because we are calling the same function again and again. So hence at one time to for sure the root will become null, and it is very important to stop that recursive call. Okay, so now here also we'll create a map. Okay, and in the map we'll check if our map does not contains same thing we'll do here also. If that key which is HD is not present in the map, then in the map just simply put on HD, which is vertex, just put root dot value. That's it. So for 0 we will insert 1. Now we will go on depth first search. Okay, we'll go on depth first search. So we'll call root dot left, and for left definitely left child level plus 1 will we have to do. Okay, and now for HD as we are going towards left, so -1. Similarly for right side DFS root dot right level plus 1 because we are going downwards, and HD plus 1 because we are going towards the right side. Okay, now in the stack call what will happen? Suppose this is our stack. Okay, so first we will go with 1 root, 0 level, 0 vertex. Okay, now we'll go for left side, which is 2 node, 1 level, -1 vertex. Again -1 is also not there, so what we will do? For -1 also we will insert what? 2. Listen it very carefully. Now what will happen? See what will happen next time. For 2 we will go towards left side, so for 4 level 2 and vertex -2. Similarly for -2 also we'll insert 4. As of now the code is not correct. Why? Because see, we are sending the level also. Why we are sending? Because it is required. How? Only with root and the vertex it will not be correct. We'll see this via dry run. So -2 we have sent. Now we'll go towards the left side, we'll return, and then we'll go towards right child, which is 5. So 5 will get inserted. So 5 will get inserted. So 5 level 3 and vertex -1. Correct. So -1 is already there, so we'll not insert. Okay, so now this 5 will get removed from the function call. Okay, now what will happen? As for 4 left child already returned, right child already returned, so 4 will also get returned to 2. So 4 will also get removed from the function call. Now this was 2's left call. Now we'll go towards 2's right call. Correct. Okay, so what we'll do? We will insert 6. We will insert level, which is 2. And we will insert vertex, which is 0. Again for 0 it's already mentioned, so we will remove this also. Correct. Now we will also 2 will also get removed because left also has been returned, right also has been returned, so this will also get returned, so 2 has also been removed. Now for 1 we'll go towards right side. Right child means 3 level 1, vertex 1 will get inserted. Now for vertex 1 3 will get inserted. Correct. Now we will go for 7 and 8. So here 7 will get inserted with level 2 and this 1. Okay, so as of now, so it's very simple. Okay, this is already present, so we'll not insert. Now we'll insert 8. For 8, the vertex is 2. So for 2, 8 will get inserted. Similarly, for 9, which is vertex is 3. So for 3, 9 will get inserted. Very simple. Then why do we even need level? See, why it is required? Suppose a tree structure looks like this. So what we'll do, you will insert 1. Why? Because for for vertex 0, this will be for vertex 1, this will be for vertex 0, this will be for vertex 1, this will be for vertex 2, and this will be for -1, correct? Now see, listen it very carefully. For vertex 0, 1 will get inserted. For vertex 1, -1, 2 will get inserted. For vertex -2, 4 will get inserted, because as of now, all are new. -1, it will not get inserted because 4 is already there, okay. 4 will also not get inserted because this 2 is already there, okay. Now 3 will also not get inserted because initially it already got inserted. But for 1, 5 will get saved. Listen, for 1, 5 will get saved because this is depth-wise call. Okay, now for 2, 6 will get saved. So when we will go at 9, later we will see, hey, for vertex 1, 5 is already there, so don't insert 9. But as per the top view, 9 should get inserted, right? Yes, 9 should get inserted instead of 5. So hence, even if this vertex has already been inserted, correct, but if the upcoming vertex node level is lesser means ki hey, for one vertex I already found the value, but its level was larger than what you have found now. So for sure this 9 will be visible instead of this 5. So hence at every call along with the vertex in DFS code, we have to go with the level as well. But why this was not needed in BFS? Because in BFS we were already doing the level wise traversal. So hence any node which we are finding for the first vertex, this is the top only. So that's the main reason we have inserted level. So now in this code, what do you think what should get changed? So now can I say, instead of directly putting, I have to check one more case, and that will be if the vertex is found for the new time, then to for sure in the map insert. But if it is already present, then check for the level also. What if the level of the current node, okay, is lesser than, in map we already have element, so map dot get what for that node which is present at that HD, okay. But how to get that level? Because in the map we to have just stored for every node, we just have a stored value. But if we have to get its level so that we can compare, when I have found for vertex 1, first time we found 5. So if I will just add for vertex 1 5, then when I again found 9, for vertex 1 it's already there, yes. So I need to compare the level. So for vertex 1, whatever node I have inserted, along with that I also have to insert its level, which is 0, 1, 2, 3. So now I will compare my 9's level with this level, correct? So suppose we insert like this, instead of only value, I will insert a list of 2 elements, key vertex like value 1 and level 0. Similarly for 5, value 5 but level 0, 1, 2, 3. Now here map.get for HD, yes it was correct HD, but instead of 0th node I want first node, which will give level. So if the current level of 9 is lesser than this, which is actually correct, then in the map please override this with 9 and level 1, okay. So what we'll do, in map we will put where at HD, but what we will put, new integer array, okay, with root value, correct, and level as well. That's it, okay. So now at the end in the map we will have for 0 1 0, for 1 5 3, okay, let's move it down. For -1 what we will have, 2 but level 1. For -2 what we will have, 4 but level 2, okay. Now this will not get inserted, this will not get inserted, this will not get inserted because -1 0 is already there. Now for 1 5 will get inserted. For 2 what will happen, 6 will get inserted with level what, with level 4. Now later on when we will go at 9, this will get overridden with 9, yes, and level 1. So see, is this the answer? Can I say 4 2 1 9 and 6? See, 4 2 1 9 and 6, correct? So now from the map, we just have to read the values of 0th index value, okay? So let's write the code for this. So here is the code in Java. First we'll make the map, okay? And in the map, we will have integer as key and integer array as value. Now in the top view, we'll call the function, we'll give the vertex and level as 0, 0, and we'll create the array list. Once this DFS array will fill the map, so we'll iterate in the map and we will, in the answer, we'll add values of 0 because first index value stores the level. So we just have to store the values, correct? Means node dot value. At the end, we'll return. What we are doing here, we are checking the base case and we are checking if that particular vertex has not been inserted in the map, then insert it, or else if it is already there, then check the level. If the current element's level is lesser than what we have inserted earlier, then update it. Okay, now go towards left side and right side as it is. So now let's run the code and let's submit this. So talking about the time and space complexity, here also we are going on every level one by one. So O of n, where n number of nodes, okay, and space wise, if it is a complete binary tree, then logarithmic of n, as we are already talking in every video, correct, how the internal stack will actually save one node from all the levels. So logarithmic of n. If it is a skewed tree, then O of n. And definitely this tree map is going to store, take our space. So for every vertex, we are going to store one element, okay. So map size will be 1, 2, 3, 4, 5. And this length is nothing but the maximum width of the tree, okay. Now, so this was your Java code. Here is your C++ code with a similar approach, and here is your Python code with a similar approach. So if you understood the DFS and BFS approach for top view of a binary tree, then you are eligible to go in the sheet and mark the next question, which is top view of a binary tree as done. So stay tuned, we will do the bottom view of the binary tree in the next video. And if you are liking the video as of now, pattern wise and both DFS and BFS approach, do hit the like button and subscribe the channel if not yet subscribed. I'll attach the sheet link and my social media link in the description. Let's meet in another video with some more interesting questions, topics and patterns. So then keep learning, take care of yourself and your family.